looks like before it gets to Zolt's desk. So I'm going to switch here to screen share mode.
Okay.
So I might be able to show with a little bit higher resolution as well what Zolt was talking about. So this first image I'm showing you here is just one of the long visual band exposures, and I think you can see right there you can see the comet tail looking about the same, but you can see the comet nucleus, instead of being a nice dot, is a little bright line at about a 45-degree angle.
And that's because it moved during the exposure, right?
That's right. So we took a long exposure. That's why we got, you need a longer exposure in order to detect all those stars, and especially the galaxies in the background.
How long was it, do you know?
Yeah, this was something like 200 seconds, something like that.
Okay.
So that's how much the comet moves in that amount of time during this long exposure. And then if I go to the next one, so then you stop that exposure, you take another one, and you see the comet has moved. That's the next exposure. Then I'll click to see the next one, and you can see it's kind of turning a corner there in the L, and I'll explain that in a second. And the next one, and the next one. And if I go to the, let's see, here's sort of the L image that Zolt was showing.
Oh, wow.
Great.
All of them together. So the comet itself is moving in a linear fashion, and the reason it looks a little bent like that is because Hubble itself is moving as well. During one orbit, Hubble goes from one side of the Earth to the other, and so that's called parallax, which you experience yourself with, something that's close to you, and you move your head side to side. The thing that's close to you moves more than something that's farther away, and so you get, that sense of, perspective. So, that weird motion you see there, it has more to do with the motion of Hubble than with the motion of the comet itself. Now, just to show you how messy the image is, to get back to your original point, I'll pull up the same version of this image. Now, this is after I've cleaned it up quite a bit. So now I'm going to switch to what that image looks like before I've cleaned it up. And what do you see here?
What a mess! So this is a raw image, right? This is what it comes out of Hubble.
Right. So we've been looking at cleaned up images, and it takes some effort. And this last one I'm showing you right now shows all the junk, before I clean it out. So what are you seeing here? You got a mixture of the real stuff, the comet, the stars, the galaxies, but then you got all these big things, these bright things here, like this big bright one going right through the comet tail. And there's an even brighter one right up near the comet. Yeah. Those are called cosmic rays. And all these little flecks, too. It looks like salt and pepper has been shaken all over the image. One of the reasons we put a telescope above the Earth's atmosphere is the Earth's atmosphere protects us from all that radiation out in space. Right. So it's great that, life on Earth wouldn't be possible if the atmosphere wasn't protecting us, but of course, you get up above the atmosphere to get above the blurring effects of the atmosphere, and now you're exposed to that radiation. So while we're taking this 200-second exposure, all this radiation is flying right through the telescope and peppering every image with these cosmic rays that you see. And then, of course, there's also detector artifacts. No camera is perfect, so there's all kinds of, in a sense, junk coming from the camera itself that needs to be cleaned out.
Bad pixels, hot pixels, things like that, right?
Exactly. And so that's why we take many exposures, is to not only gather information in different wavelengths of light, as Zolt described, to make a color image. We have different filters, but we also, within a filter, take multiple exposures so that we can combine them. And by comparing the images to each other, if I take 3 or 4 images in a row that should be identical, the stars and the comet and the galaxies will all be in the exact same place. But the cosmic rays will be in random locations, so that you can compare the images and say anything that's in all the images must be real, and anything that's in random locations must be cosmic rays, and reject it, and that's how you get a clean image. So you can see we are contending with quite a bit here, and sometimes you're lucky in the sense that you really don't want a bright cosmic ray going right over the top of your image. It might be tough to clean out. You might notice in some of these images, I'm just going to click through to one. For the red exposures, we didn't take as many. We only took 2, and that makes it harder to clean up. And you'll notice right above the 2 comet trails here, there's a pretty bright cosmic ray. There's that really bright one. I couldn't get it completely cleaned out. So it's just sort of a cautionary tale that no astronomical images are perfect. There can be artifacts that hanging around that you might look at an image like this and get excited about and think, well, that's something to do with this comet, when in fact it's just a random cosmic ray that couldn't get cleaned all the way out.
Well, I was going to say it might have been a spaceship or something right behind it. But
it's an important point to make, because we have been inviting. Normally, historically, it's mostly professional scientists who've been getting into our archive. People who use Hubble getting into our archive, but we have been inviting the whole world in there. to have a look at our data. And of course, it just requires a few more skills in terms of understanding what you're seeing and interpreting data. And looking at raw data, as I pointed out in the last one, there's a lot of junk there. And the untrained eye might get excited about what they see, thinking that this long streak is something more exciting than just a cosmic ray. But and that's why we actually provided, I actually posted our cleaned up images. There's a link to it from the blog and also from the press release. So people who are interested in playing with the actual data in FITS format, if you don't know what FITS format is, you probably don't want to do that. But a lot of amateur astronomers, and including professional astronomers, are familiar with that. And so, kind of getting at the data behind the image, you can follow that link to actually get my version of the data, which took a lot of careful processing. Unfortunately, our routine pipeline doesn't do such a great job, so it really requires a lot of offline